Research interest revolves around the areas of distributed computing, machine learning, and mobile and embedded systems. Lately, he's also tapping into the areas of NLP and large language models.
Can you hear me? Yes. Thanks, Pranith, for the introduction and for the invitation. Right, so I'm going to talk about how we can uncover low-rank structures via trainable decompositions. A bit of an introduction, quick one. Researcher at Brave Software. I'm also a visiting researcher in the University of Cambridge. Before that, I was at Samsung AI in Cambridge, so very focused on Cambridge, you can see. I did my postgrad there, and I also was an engineer at CERN in Switzerland. My research interests revolve around the areas of distributed ML, mobile systems, efficient deep learning, as well as federated learning, as expected. Right, a few things about Brave, because I talked to a few of you and you didn't know. This is not an advert. Don't use it, I don't mind. Right, so Brave offers an alternative to big tech in terms of the web components. So we have the main product is a browser, and we also have an independent search engine, so it has an independent index. The only alternative is Google and Bing effectively to that. And there are a bunch of other products. Right, Brave browser is pushing for privacy by design. So we have integrated ad blocker, and we block third-party tracking and fingerprinting by design. It's Chromium-based, it's open source, and it's available across different platforms. So this privacy sensitivity is creating certain challenges for us. So individual users cannot be addressed. Whatever ML we're doing, it needs to be privacy preserving, and it needs to happen mostly on the foreground. It cannot interfere with the quality of experience to the users. FL participation, since we are anonymized, we don't have a persistent channel to different clients, so it needs to be client initiated effectively, and certain users cannot leave the device at all. So FL is the only way to move forward with differential privacy or other privacy guarantees. Right. So I'm going to first refer to a bit of a background and motivation about our work. Then I'm going to introduce Maestro, which is uncovering the low-rank trainable manner. And then I'm going to talk about certain challenges and future direction of this work. Right. So everybody knows that neural networks have been getting more and more heavyweight as they become ever more accurate. We're entering the era of hyperscale models, and this takes its toll on the computational side of things. So we have new use cases being put forward, such as self-driving by Tesla, or image in-out painting, such as the Adobe Firefly, web page interaction with various LLMs, such as Brave Leo, or even the voice assistant being put forward by Google on the latest Pixel. So deployment trends include different architectures than in the past. So we have LLMs and transformers, which is apparently all we need. Stable diffusion models, or even neural radiance fields. So at the same time, we have devices that do not have a single model deployed, but multiple models cohabitate the device at the same time, either in the same app or across different applications, and they run at the same time. Indicatively, you can find, like nowadays on devices in your pockets, more than 50 models being resident. And also the privacy has become very important in the agenda of companies and regulators. So we move to techniques into that relate to local private inference, or even on-device training and personalization. So there are certain bottlenecks when you're running workloads on device. These bottlenecks can vary from energy boundedness, so you can have workloads that cannot really run for a long time in the background. An example here is Android doze, which is the mechanism that Android uses for putting applications to sleep. So you need to opportunistically train as you have devices as you have applications in the foreground. You have memory boundedness. So for example, if you want to run an LLM device, you can see that it is largely memory bound. So the accelerator is waiting for the memory, for the weights to be brought from memory to on-chip memory. And also there is the compute boundedness. So when you're fully utilizing the compute throughput of your device, then you're effectively bounded by the theoretical throughput of your device. Right. When we're going distributed, the story is slightly different. So on the distributed training, for example, of hyperscale models, we have the bottleneck being the accelerator interconnection inside the data center. And outside of the data center, you have the wireless link being usually the bottleneck, and specifically the upstream communication. So all these trends, as well as the model size being scaling faster than the hardware advancements, pose for a requirement for algorithmic and infrastructural contributions to sustain these workloads. These include algorithmic contributions in the area of stochastic execution of graphs, such as mixture of experts or early exit networks, bringing down the traffic either in network or like from main memory to on-chip memory. And you can see quantization and low-rank approximations being towards that front. Then more specific solutions to LLMs, such as speculative decoding or token skipping, as well as workload offloading, where you can use, you can leverage external resources that are faster in order to run your workload. Right. Some prior work. We had NeurIPSET 2021 Fjord, which is a resource-aware federated learning training scheme for tackling system heterogeneity through order dropout. I'm going to talk about order dropout, but effectively it's a method for controlling the model footprint in comparison with the resources that you have on device. And then we generalize these into Fedoras, which stands for Federated NAS. It's similar to what Alexei presented before, but it also accounts for the training variation and the capability of devices. So NAS allows for more degrees of freedom in the architecture. And going back to Fjord and order dropout, a brief introduction. It's a mechanism for order or importance-based pruning based on sample-nested training. It enables the extraction of submodel training without the need to retrain. And it's parameterized mainly by the p-value, where it ranges from 0 to 1. So at each batch that passes from your network, you take the first p by KL, KL being the width of the model, and the rest is being dropped. So you train that with or without knowledge distillation. Right, so the question is, what if we leverage decomposed representation in a trainable manner in order to target model efficiency? And this is where Maestro comes in. This is fancy icon, comes from OpenAI's DALL-E. So instead of operating on the width of the model, now we're going into the low-rank decomposition of the model. So we first run a decomposition, an SVD decomposition on the layer of the model, and then we're using order dropout effectively on the low-rank representation in order to be able to select to sample the ranks that are being trained, and then progressively pick the more important ranks and remove the redundant ones. Compared to Fjord, we're operating on the decomposed weights, and we're doing independent sampling per layer. So you don't have a uniform p-value anymore, but you're sampling independently per layer. So the training process looks somewhat like this. You start with the SVD decomposition I said before. It applies to different types of networks, linear layers, convolutional, or even transformer layers. You have BI being I and B, sorry. I is the layer you go for each layer of the network, and B is the rank that you're selecting. And you're computing the loss based on two components. The first one being the learning objective, of course, on the sampled ranks. And then we have a hierarchical group lasso loss, which eliminates progressively the unimportant ranks. That means that the unimportant ranks are pushed towards 0. And then we're progressively shrinking, based on these assumptions, the the network by pruning away the unimportant ranks based on the epsilon hyperparameter, which is thresholding effectively what your effective zero is. So this method has some nice theoretical guarantees that for uniform data and linear case, Maestro recovers SVD. And for the linearly transformed data set, Maestro recovers the PCA of the identity mapping. In terms of empirical results, we ran our algorithm on several datasets and models, including vision and text. The training behavior you can see on the left side of the slide. You can see how the total ranks, so the importance across all layers, evolves over training. And you can see that it stabilizes, and also how the ranks per layer are evolving across the network. You can also see for different lambda values. Lambda is the hyperparameter between the group Lasso loss and the actual loss, the objective loss. And last, you can see the convergence behavior of Resident 18 on CFAR 10, which is quite smooth. We compared with various baselines, including baselines from the low-rank decomposition, from unstructured pruning using lottery ticket hypothesis, being imp and rare gems, binary quantization with XORNet, and you can see that we have competitive accuracy for the same amount of flops or even less. And you can also see how we compare with such methods in the case of transformer architectures. And last, we did sensitivity on the impact of the specific selection of the lambda hyperparameter, so the balance between the two objectives. And you can see how we can trade off accuracy with the number of parameters, because it pushes less of the unimportant ranks or more. And then the ablation study of how the group Lasso and the progressive shrinking affects our method. Of course, one can actually deploy either the model that is the result of the progressive shrinking, or even go beyond that, so shrink the model even more by sacrificing some of the accuracy. The way that we do that is that we rank across all layers the importance of the method, and then we start shrinking by the least important ranks. And you can trade off this way accuracy with latency. So you can see for two different models and data sets how this behaves. The SVD model here represents a model that is just factorized through SVD, and we're selecting the ranks that were the output of our method. So it's a post-mortem, let's say, application. And you can see that it is significantly worse. So some challenges of future directions. On the sustainability side of things, we have not really evaluated the energy impact, but we're using model size as a proxy. However, when we're talking about deployments, especially federated learning deployments, where you're training at the edge energy sources are not as green as the most efficient data centers in the world coming from Google or from Meta, for example. So we need to be careful and not use that as an excuse, for example, to become less green. On the guarantees, there is no inherent guarantee about the footprint of the model that we end up with. And the greedy search that I described before for the accuracy latency trade-off is just a starting point that works sufficiently well in our use case. Of course, after pruning, fine-tuning may get some of this lost accuracy back if you have still access to the training data or some training data. And on the scalability side, well, we have hyperscale models and LLMs making their way into production, so they can have a significantly larger search space. So going layer by layer and sampling in that manner might take its toll on the algorithm. So the non-uniform sampling, a non-uniform sampling technique in combination with the use case that you're deploying for may increase the utility and accelerate the training overall. So a shout out to my wonderful collaborators, Samuel, Shoshank, and Honki. And thank you. I hope I'm in time. Thanks.
we have any questions? Then maybe I can ask Eric to set up meanwhile. Thanks again.